All right, so today I have actually been really looking forward to this lecture because today we are going to talk about the connections between Riemann sums and definite integrals, and it's just awesome. Okay, so objectives, do Riemann sums classwork, homework. I actually changed to definite integrals worksheet later. And lecture is this lecture, which will be linked. So part one is connecting Riemann sums and the definite integral. So what we know right now that Riemann sums approximate the, let me write, not in red, in black, area under the curve. That's not how you spell curve. The curve between 2 points. That's what the Riemann sum approximates. We know that it uses rectangles, either trapezoids, midpoints, different sorts of rectangles to approximate the area under the curve. What we don't yet know is what a definite integral represents. So here's our big piece of new information that maybe will blow your mind, but the definite integral represents the area under the curve of a function. So just like we know that the derivative is the slope of a tangent line at the point, the integral is the area under the curve of a function, the exact area, not an approximate area like a Riemann sum. So in other words, Riemann sums are a method for approximating the area under the curve between two bounds, but we can find the exact area under a curve between two bounds by taking a definite integral. So a reminder, a definite integral takes the following form: integral from a to b of f of x dx, where f of x is called the integrand and dx is the variable of integration. A is the lower limit of integration, and b is the upper limit of integration. Okay, and reminder, we can evaluate definite integrals using the fundamental theorem of calculus, which states that if a function is continuous on a closed interval a to b, then the integral from a to b of f of x dx is equal to f of b minus f of a, where the derivative of small f of x, our function in here, is equal to large f of x, right? So we can go from the derivative to the initial function, plug in our bounds, and evaluate. Okay, so the fundamental theorem of calculus, reminder, is just the way that we evaluate definite integrals. It's just saying plug in your bounds. Okay, so there's our reminder, there's our new information, and now we're going to think about this in terms of an example. So let's draw a picture of what's actually going on. Say we wanted to find the area under the curve f of x equals 1/2 x squared between 2 and 6. First, let's approximate this area using a right Riemann sum with n equals 4. So go ahead and pause this video and see if you can do this problem on your own. So we know, hopefully you paused it, now I'm going to go into the explanation. Delta x is equal to 6 minus 2 over 4. 4 over 4 equals 1, so delta x is 1. That's convenient for us. Let's draw our function. We actually don't need a negative axis because we are talking from 2, 3, 4, 5, 6. Our unit is 1. The delta x is 1. Sketch some rectangles. I'm going to redraw my function to make it a little bit easier on myself to see those rectangles. There we go. And now we are going to have n equals 4 rectangles. So 1, 2, 3, and 4. And then we know that we are using the right endpoints. So let's switch colors. Feeling blue today. Here's my right endpoint. Right endpoint, right endpoint, right endpoint. So my right endpoints are going to be f of 3, f of 4, f of 5, and f of 6. Okay, so let's evaluate those. F of 3 is equal to 1/2 times 3 squared, which is going to be equal to 9/2. F of 4 equals 1/2 times 4 squared, which is equal to 16/2, which is 8. F of 5 is equal to 1/2 times 5 squared, which is equal to 25/2. And f of 6 is equal to 1/2 times 6 squared, which is 36/2, which is equal to 18. And now for our rectangle areas, let's go ahead and switch back. And we know that those areas are going to be width, which is 1 times height, f of 3, which is 9/2. 1 times 9/2 is 9/2. 1 times f of 4 for my height is equal to 1 times 8, which is 8. Rectangle 3 is 1 times f of 5, which is 1 times 25/2, which is equal to 25/2. And then rectangle 4 is 1 times f of 6, which is equal to 1 times 18, which is 18. So my total area is going to be 9/2 plus 8 plus 25/2 plus 18. And that is going to give me an approximate area of 43. Okay, but now we know that the exact area under the curve is represented by a definite integral. And so the area under the curve, f of x equals 1/2 x squared between 2 and x, is exactly equal to the integral from 2 to 6 of 1/2 x squared dx, which we can write as 1/2 times the integral from 2 to 6 of x squared dx. That is going to be 1/2 times x cubed over 3, which is equal to x cubed over 6 from 2 to 6. We can go ahead and plug in our bounds here, and then we are going to get 6 cubed over 6 minus 2 cubed over 6. I should have my calculator out, but I do have my phone right here, so I'm going to do a little quick 6 times 6 times 6 equals 216/6. Minus 2 cubed is 8, minus 8, 6 is equal to 216 minus 8, which is 208, divided by 6, which I should use my calculator for. I don't know why I didn't just reach in my bag. I don't even remember what I said. 216 minus 8, that's 216 minus 8. 208 over 6. And that is going to simplify to 208 divided by 6, 104 thirds. So that is approximately equal to, let's compare, 34.6. So does it look like our approximation was very good? No, it does not. But that is to be expected because look at all this extra area that we accounted for. Like, that's a decent amount. So from our picture, it is clear that the approximation will get closer and closer to the exact area as the number of rectangle increases, okay? So if we did the same thing and we had more rectangles, I'm gonna clear this out. I'm gonna scroll down a little bit and I'm gonna re-sketch that picture for us. So again, we have a parabola. We only have 2, 3, 4, 5, 6. We only have 4 rectangles. And again, we had a lot of extra area, okay? However, the approximation will get closer to the exact area if we used more rectangles, right? Because then we're using less space above or below the curve, and we're getting closer and closer to this actual curved line, right? So if I had like smaller slices, then you could see your approximation is going to get closer and closer and closer to that curve, and you're going to account for much less extra area. So following that train of thought, the best approximation would be if we had an infinite number of rectangles. Well, we can't set n equal to infinity because infinity isn't actually a number. But thankfully, we have the notation for when we want something to get really, really close to infinity, maybe approach infinity. Limits. So the limit as n approaches infinity of any Riemann sum is equal to the definite integral. And so in math terms, we can go ahead and write that out as the following. The limit, if my pen would work, I could. The limit as n approaches infinity, where n is the number of rectangles in our Riemann sum, of the sum from I equals 1 to n number of rectangles of f of x sub I times delta x. So that is saying the height of any rectangle times the width is equal to the integral from a to b of f of x dx. And that dx, that is our delta x. Our dx is delta x getting infinitely small. And that's where that notation comes from. N getting really large and delta x getting really small. So, you know, a larger number of rectangles with a smaller and smaller width. N getting really large. And that, my friends, is what a definite integral is. It is the area under the curve. That's pretty cool. Like, really just let that sink in for a second. That's so cool. So knowing that the definite integral represents the area under a curve is very powerful and will eventually lead us to being able to solve a whole bunch of application problems. And you should be nervous about the way I said that. So we're going to start simply. For instance, given that something is traveling at a constant rate of 5 meters per second, what is the distance traveled in 4 seconds? Well, we know that rate is dependent on 2 things, and those 2 things are change in distance and change in time. So if we were to write an equation, we would have rate equals delta d change in distance over delta t over change in time. Okay, and using the information in the problem, we can easily solve for distance. So we know that given something is traveling at a constant rate, so our rate is 5 meters per second, is equal to the distance traveled. We want to know delta d, and we know that it travels that far in 4 seconds. So we're going to multiply up by 4 seconds. And we know that 5 meters per second times 4 seconds is going to be equal to 20 meters. And that will be our delta D. So we can also draw a graph of this, okay? So I'm going to scroll down a little bit, and we're going to draw a graph where we have rate on our y-axis and time, as always, on our x-axis, okay? And we know that something is traveling at a constant rate of 5 meters per second. So constant rate means that it's not changing. Our line is going to be nice and straight. And we want to know the distance traveled in 4 seconds. So there's 4 seconds and there's 5 meters per second. Okay. To get distance, we need to multiply rate by time. On our graph, that is multiplying the base, which is the change in time, by the height, which is the rate. Okay? And so we can see that what we are actually doing to find distance would be to find the area under the curve. I'm going to say that again, okay? To get distance, we need rate times time. If we look at our graph, we can see that rate times time is going to be the height times the base, which is going to be the area under my curve. And so therefore, we can see that the area under the rate curve is equal to net change in distance. And again, this is going to be 4 times 5, and we're going to get the area under the curve equals 20 meters. Okay, so more generally, we can start to wrap our minds around the idea of an integral representing net change or an accumulation of change, okay? Because in this problem, over 4 seconds, our net distance, or change in distance was 20 meters, okay? So this area under the rate curve could have been represented by an integral, a definite integral. We know that now, area under curve, definite integral, net change or accumulation of change. In this problem, we had a net distance or change in distance of 20 meters. Okay, so therefore, whenever some problem refers to the net change of something, we are asked to calculate, how much of that thing has accumulated over time. We can solve the problem using a definite interval. For example, the temperature of the soup is increasing at a rate of R of t equals 30e to the negative 0.3 t degrees Celsius per minute, where t is time in minutes. At time t equals 0, the temperature of the soup is 23 degrees Celsius. How much has the temperature of the soup increased in the first 5 minutes of cooking? So in order to evaluate this, we are looking at how much has the temperature of the soup increased in the first 5 minutes. Okay, so net change of the temperature of the soup indicates an integral from 0 to 5 minutes of cooking of our R of t function, which is turned out to be the integral from 0 to 5 of 30e to the negative 0.3 t dt. We're going to pull out a 30 integral from 0 to 5 of e to negative 0.3 t dt, and then we are going to evaluate that integral as equal to negative 30 over 0.3 times e to the negative 0.3 t. Look up your e rules if you were confused by that integration process from 0 to 5. And then I'm actually just going to go ahead and approximate that. So you can plug that into your calculator, and that's going to get 77.7 degrees Celsius. Okay. And then what is the soup's temperature at 5 minutes? So this is no longer a change, but in the actual value. Okay. Right. So in the first question, we're asked, how much has the temperature of the soup changed? In the second question, we're asked, what is the soup's temperature at 5 minutes? And that means that we have to add an initial condition, since we are asked for a value and not a rate of change, or not a net change, okay? And then if we look at that, we can see, oh, at t equals 0, the temperature of the soup is 23 degrees. So the soup's temperature at 5 minutes is going to be 23 degrees plus however much it has increased, which is going to be equal to the integral from 0 to 5 of R of t dt. So we can see that the soup's temperature after 5 minutes is going to be whatever it started with plus whatever it increased by. Okay, that's that 23 plus whatever it increased by, which is equal to 23 plus 77.7 degrees C, which is roughly equal to 100.7 degrees Celsius. Okay. And then if we scroll down a little bit, we have one note which says, what is given and what are we trying to find and what to use, okay? And so this table will not only help us as we begin to solve application problems, but it also highlights the connectedness between integrals and derivatives. Okay, so if you're given a quantity and you're trying to find a rate, you want to use a derivative. If you're given a rate and you want to find a quantity or a change in quantity, you're going to use an integral. Okay, so this table, starting to think about these applications is definitely going to be tricky at first. And then let me see, I have it up here somewhere. Here's worksheet 4.6 that is your homework, which gets at these ideas. And so if you have a hard time with the homework, it's okay. Remember, just try your best, come to class, and we will go over all of it together. So other than that, I don't have anything for you guys. Hopefully you were as excited about this application and like little light bulbs went off, maybe some fireworks or something, because this is such a cool application. And like, this is literally the tip of the iceberg. And as soon as we get over this hump, then like open your eyes to the world of applications of integrals. But anyway, that's coming. So get excited and bring any questions you have to class. Thanks guys, have a great day.